Okay, so we have a problem here where a person is, say, going to throw a baseball into a moving boat. And so on the left-hand side, the person is standing at the top there. They're at 8.75 meters above the origin, and they're going to be throwing this baseball at 15 meters per second. That's the velocity at a 60-degree angle to the horizon. And so the baseball is going to be thrown, and it's going to make a ballistic trajectory, and it's going to end up hitting where this X is on the bottom, where the X is. That's where it's going to hit. But we also have a boat, and the boat's over here on the right hand side, and so the boat's going to be moving to the left, and the ball's going to be moving to the right, and we want them to meet at the same time. Okay, so the question is, at the time the person throws the ball, at that time, how far away should the boat be so that they can intercept the thrown baseball? Okay? All right, so what we have here is basic setup. Now, like I said, I'm not going to use basic formulas for computing this. We're gonna solve this using calculus, either integral or differential calculus. So because this is a two-dimensional area or two-dimensional plane, velocity and acceleration and position are all things that are vectors. So they're in this case here two axes or two dimensions, so x and y. So we're not doing 3 dimensions here, but so these things are vectors. So what we're going to do is we're going to plot out the velocity in x, the velocity in y, and the r is the position in x, and the position in y. So we're going to use this to figure out how far away should the boat be when the ball is thrown. Okay, so we look up here at the top where it says 15 meters per second, 60 degrees. So what I want to do is I want to break this velocity vector up into its x and y coordinates. So at the bottom here, at the horizontal part, that would be 15 times the cosine of 60. It's cosine because the bottom is adjacent to the 60 degrees. So so cosine, of course, is adjacent over hypotenuse, whereas sine is opposite over hypotenuse. So what we want to do is we want to compute the cosine. So we're going to say 15 times cosine of 60 equals, and this is 7.5 meters per second. And so that's how fast the ball is moving in the x direction, right? And up in the up, down, or y direction, it's moving 15 times the sine of 60, and that's 13. So this is 13 milliseconds. So it's moving 7.5 meters per second to the right, and 13 meters per second it's moving up. Okay. So we've taken that vector, the velocity vector, and we've broken it up. So what I want to do now is I want to go down to my the velocity x and the velocity y, and just plot those initial points. Those are the initial conditions. So the velocity in x is, and I'm just going to put it here, and I'm going to write 7.5. Okay, and this is in meters per second, and this obviously is also in meters per second. So the velocity in x is 7.5, as you can see from here, and then the velocity in y starts out at 13. So we'll just write maybe here or something, and we'll say 13 meters per second. Okay, so let's look at the velocity in x. Is the velocity in the x coordinate, in the x dimension, is it going to slow down? Is there a force that's going to slow it down in x? No. There is gravity, but gravity only affects it in the y direction. It doesn't affect it in the x direction. So theoretically, right, this x velocity doesn't change because there's no force acting upon it. in the x direction. So it's 7.5 meters per second. So it's just going to keep doing that, keep doing that, keep doing that until it hits the ground, and that's our time. So what we'll do is we'll just sort of like write. Maybe I'll change that to black here, and so this is our time. We'll call it t. The time that the ball hits the ground. Okay, but do I know what that is? No, I don't. Okay, so remember, so back again. So the velocity in x, it's going to start at 7.5 meters per second, but it's not going to change. So this is the graph. So as time is changing, right? 1 second, 2 seconds, 3 seconds. The velocity in x is not going up or down. Okay, because acceleration doesn't change in the x. All right, now in y, it's starting at 13 meters per second, but is the velocity in y changing? Yeah, it's changing due to gravity, right? So what we're going to do is we're going to put a line here like this. And this is acceleration due to gravity, which is, I'm going to write here, negative 9.8, negative 9.8 meters per second squared. So that's the slope of this line. This line, the slope of this line is acceleration, okay? Because this is velocity as a function of time. So it's negative 9.8 meters per second squared, but the line here is it's a slope. This is a linear. This is just a line. So obviously it's not like a second degree or third degree or fourth degree. It's just 1 degree, right? It's a constant acceleration. So we're gonna say negative 9.8 t, right? So as time is changing, and, in 1 second it's negative 9.18. It's 1 times negative 9.8. 2 seconds is 2 times negative 9.8. 3 seconds, 3 times negative, et cetera, et cetera. Okay, so that's the slope of this line. So it's negative, which makes sense, and it's not curved, so it's a straight line. Now this line here, does it have a y-intercept? Yeah, obviously the 13 is a y-intercept, so we're going to say plus 13. So this is the function for this line. So the acceleration in y is actually negative 9.8 t plus 13. Okay. Now, this point, if I do this point here, you may wonder, what's that point? Well, remember this ball is going up in the air, and then it's going down. So this point here, the yellow right here that I just drew, that's actually at the ball's highest point. So the ball's going to go up, 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 and so right as it's about to go down. So this is at its high point, or you could call it like the apogee. So I'm just going to write that down. Yeah, this little point here is the ball's apogee. Okay. And then the ball's going to start to come down, 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 and then it's eventually going to hit the ground. Okay, and so at some time, right? At some time it's going to hit the ground. Now, do I know when it's going to hit the ground? No, I don't. So in order to figure that out, we're going to need to look at not velocity, but position, right? So when is the ball going to hit the ground? Well, it's going to hit the ground when the position in y is 0, right? Because the position in y, could be, well, it's initially 8.75, and then maybe it goes up to 9 or 10 or whatever, but then it's going to start coming down. And once it hits 0, well, then it hit the ground, okay? So what we want to do is we want to take this velocity in y, this function, hit the negative 9.8 t plus 13, that acceleration function that we have over here, and we want to integrate it, right? So we're going to take this function here, and we are going to, down here, we're going to integrate it. We're going to integrate that function. And once we do that, then we'll have our y function. So before we do that, what is the initial position in y? Maybe in x and y. Maybe we'll do both of those. So if you look up here where the person is standing at 0, 0. So the x position, initial position, is actually 0. So I'm going to write that. That's his initial position, 0, 0. And then y, where's y at? Well, y is he's 8.75 meters above. So we'll say here, like right here, we'll say 8.75. And this is in meters. This is in meters. Okay, so in order to take this velocity down up here and then turn it into a position, I have to take that function, the negative 9.8t plus 13, and I have to integrate it, okay? So let's do that down here. So I'm going to do the integral of negative 9.8t plus 13, okay? And if you integrate that, you end up with negative 4.9t squared plus 13t. Well, you end up with that, but then I have to add in my initial position, which was 8.75 plus 8.75 plus 8.75. So the integral was negative 4.9t squared plus 13t. But then I had to add in the initial position, which is also called the constant of integration, which is that. So you need to put in your initial position, or else you don't know where the graph is. Yeah, you have this, this parabola, but is it up? Is it down? It's like where is it? Where is it at? Where is it actually hitting the y-intercept? And so now that we know, if we know our initial position, which we do, then it can help us like tie it down. Okay, so now we have this function, and we can just sort of like, do something like that. And where it hits, right here, that time, so because the x-axis is time, and the y-axis is our position in y. So basically we have two functions, right? We have, and I'm going to highlight them using this highlighter. So we have this function here. And then I have time, and then I have where it equals 0. So I'm going to change that to maybe this color. That. So there's two functions. There's the negative 4.9t squared plus 13t plus 8.75, and then there's the function 0, where y equals 0, okay? And what I want to know is where do those functions interact? So what I can do is I can just set them. I can just say negative 4.9t squared plus 13t plus 8.75 equals 0. So this basically says I have a function over here and I have a function over here. Where do they equal? Where do these two lines intersect? Okay. And obviously, you can just solve this for t, and if you do, you get t equals 3.21 seconds. So if you solve for t, you get 3.21 seconds, and so then I can just backtrace that. I can say here it's 3.21 seconds. Here I could also say this is 3.21 seconds. Over here, 3.21 seconds. And even over here, 3.21 seconds, okay? So now we know the time. Great. Now I want to know how far, what is this distance right here, the D1? So how far did the ball travel from when the person threw the ball to when it hit the ground? How far is that? Well, if you look over here at the velocity in x, Vx, I knew the ball was traveling 7.5 meters per second, and it keeps traveling at that velocity until it hits the ground. When it hits the ground, t, well, it stops, right? The velocity stops. So, and if you remember, this area, this area under the curve is actually equal to the amount it changed. So this area equals, what does this area mean? Whoops, sorry, go back. Is the change, we say delta, the change in the ball's position. So it's not, it doesn't tell you where the ball is, it just tells you how much it changed. Okay, so what we can do here is, obviously this is a rectangle, so you could multiply 7.5 times 7.5 times 3.21. All right, let's do that. So 7.5 times, let's just do this, 3.21. That equals 24.08 meters. So the area under this curve is 24.08 meters. So that's how far it changed. But what you want to do is you want to know how far it changed. Well, you want to know where it's at now. So because it started here at 0. So remember, the initial position was actually 0. The ball was actually at 0. So if you take 24.08, which is how much it changed, plus the initial position 0, obviously that means the ball is now 24.08 meters from the origin. Okay. So we now know that this D1 is 24.08 meters. Okay. Which is great. And we know the time. The time was 3.2. It takes 3.21 seconds to hit the ground. And in that 3.21 seconds, the ball has traveled 24.08 meters in the x-axis. Now, it still doesn't tell us about this boat over here. Like, how far away should it be? Okay, so we know a couple things. We know that the boat has to travel 3.21 seconds because, remember, as soon as the ball is thrown, the boat's gonna start moving. Okay. So the boat is going to be moving, or is going to be traveling 3.21 seconds, right? So over this time here, maybe I'll change this to a different color. Between here and here, he is going to be going 3.21 seconds. Okay. It's going to take him 3.21 seconds to get from where he's at to the ball, to where the ball is going to land. And we know he's going 0.45 meters per second. So I basically have a time, and I have a velocity. And what am I looking for? Distance. So if you remember, velocity, let me just change this here. Velocity is equal to, of course, distance over time, but I'm looking for distance. So because I'm looking for distance, I can change this formula to distance is equal to velocity times time. And I know the velocity, which is 0.45 meters per second, and I know the time, 3.21 seconds, and so therefore I can just do that math. And I end up with 1.44 meters, 1.44 meters, okay? And so that's what you could write here. Let me change that to black. 1.44 meters. And so the question is how far away should the boat be from the origin the moment the person throws the ball? Well, then that's just doing some simple addition, right? All you have to do is 24.08 plus 1.44, and you end up with 25.52 meters. And that's the answer. So when the person, so to recap, when the person throws the ball, at the instant the person throws the ball, the boat should be 25.52 meters away and traveling at 0.45 meters per second, And if that's true, then the ball and the boat will intersect at exactly the right time, and the boat will like catch the ball. Okay, so that's it. So you can see, just to recap, I solved this problem using really just either geometry here, where I was just multiplying the area, the base times the width to get the area, or I was using functions, deriving functions, or I was using integration to derive other functions, or differentiation. So I didn't actually have to use any of the quote-unquote normal physics equations. I just solved it really using either geometry, differentiation, integration, or basic algebra.